So the first thing I would like to do is define what is this density property. Okay. So definition was given by Varolin in the year 2000. And we start with X, complex manifold. F will be manifold. And we say as the density property from now on shortened as DP. If the Lie algebra, and if you're scared of Lie algebras, you can just think vector space. So this is not the definition, but it is equivalent, generated by complete holomorphic vector fields. Vector fields. It stands in the Lie algebra. Algebra of all vector fields, of all holomorphic vector fields. So let's have a look at this definition for a moment. So I'm dealing with complex manifolds and I'm dealing with holomorphic objects on this manifold. In particular, now we have holomorphic vector fields. And all my manifolds going to be complex manifolds, and all the vector fields, all the functions, everything is going to be holomorphic. So I will start skipping these objectives. Complex and holomorphic. A manifold is always complex. A vector field is always holomorphic. A function is always holomorphic. And so what are we doing here? We're looking at complete vector fields, and we generate the Lie algebra. And if you're not familiar with Lie algebra, just think, okay, you generate the vector space. So you just take sums, linear combinations, and you get something. You take the closure, dense. You take the closure, and you want to be able to approximate this way all vector fields, all of them. So this property looks very much a property about vector fields. In fact, it is a property about vector fields, but in fact, it's also a property about automorphisms. The flow of a complete vector field, C the F will be complete vector field, is an automorphism. So the density property is not just about vector fields, is in fact very much needed or used to study complex manifolds which have a large group of automorphisms. But this property somehow means that we have a lot of complete vector fields and a lot of automorphisms. So let me just give you a quick list of examples of manifolds with density property. And the first one, I always like to say it, is if you just take any compact manifold. This is extremely boring. Why is this not interesting? Well, because every vector field on a compact manifold is complete. So the property just doesn't say anything. Okay, absolutely nothing. And in fact, most compact manifolds don't have a large group of automorphisms. So why am I saying that having a lot of complete vector fields implies lots of automorphisms? Well, that's still true. The point is that here is not having, you don't have a lot of complete automorphic vector fields. Simply whatever you have, well, they are complete. The density property becomes way more interesting when you add the condition that your manifold is also Stein. You can think of Stein as just a manifold which admits lots of holomorphic functions. So X to C. And so the next examples are all going to be Stein manifolds with the density property. So the first one, the classical one, is Cn where n is greater than 1. And this was given by Anderson and Lambert in 92. And also this result kind of gives the name of the theory in which density property comes in, which is the Anderson-Lambert theory. And I just want to point out that the case n equal 1 never has the density property, meaning that anything of complex dimension 1 cannot have the density property. You really need at least 2 dimensions. Another example is Cn times C star, meaning C minus the 0, to the k when both m and k are greater or equal than 1. And this was by Marolin in the same paper where he did introduce the density property. So observe, okay, if I were to take k equals 0, then I just packet Cn. And instead, if I were to take n equals 0, I'm left with C star to the k, which in fact is still not known. So square root of this. So C star to the k is still not known, and not still meaning 23 years ago, but even more. So I mean, of course, with different language, there were already questions regarding the automorphism group of C star to the k in the late 70s, and there are even a couple of wrong proofs in the literature. So it's still very open. And then maybe the first big step into, these are kind of sporadic examples. Okay, compact, sure, lots of them, but not interesting. Cn times C star, well, do you really need to codify this in this definition? These are just very concrete examples. You can work on them directly. So maybe the first big class is linear algebraic groups. And they're affine homogeneous spaces. Spaces of dimension greater than 1, again, because dimension 1 doesn't work. And this is the work of many people. Zelli, Dvorsky, and Kaliman deal with the affine, with the quotients, so the homogeneous spaces, while Kaliman and Kucherbach proved the initial part about linear algebraic Lie groups. So basically, you take a group of matrices, linear algebraic Lie group, group of matrices. This happens to have the density property. And also, if you take a quotient, and this quotient happens to be an affine manifold, and dimension greater than 1, this also has the density property. Okay, and you can think that what are the complete vector fields there? Well, you can take left invariant vector fields, but then you can multiply them by functions. That's more or less the idea. And then we have a lot of other examples, which maybe don't come in such large classes as this one. And I'm just going to give basically a list of names. So we have Danielewski surfaces, and very bigger. Let's keep it. Surfaces. So this was again by Kaliman and Kucherbach. And then we have some Giza tooling surfaces. And this is a work of many papers, because in some papers some were proved, in some other papers other were proved. Kucherbach, which I'm going to start to shorten. Then we also have topological amorphous spaces. Again by Andres. And then we also have the Corres-Russell QB. So they're not exactly called like that. And this by the one by. So these are just names. If you know what they are, it's a reminder that these are the density property. you don't know what they are, I'm just basically trying to convince you that Stein manifolds with the density property are not that uncommon. The property is very strong, but in fact, many manifolds have this property. Okay, and if you have more questions, maybe you should ask about them. So again, as part of introduction motivation, what is the density property? Why is it relevant? Maybe I also want to give some consequences. So not just, okay, these are examples, but also, okay, I have a Stein manifold with density property. What can I do with it? So maybe this. So we take X, Stein, and density property. Then maybe the first consequence, which goes back to this remark, is that the automorphism group of X, so complex automorphism again, is infinite dimensional. So you can think about it as a infinite dimensional Lie group, more or less. Yeah, so it is indeed very large. Okay, at least when we assume that it's Stein. And in fact, we can even do more, or let's say we can do very specific things with this infinite dimensional group. For instance, we can do jet interpolation. So what does it mean, jet interpolation? It means you can prescribe derivatives. Yeah, you fix a finite number of points, and in each of these points, you fix a finite number of derivatives. There is an automorphism which has these derivatives at these points. Okay. So that's what I mean by jet interpolation. So this fact by itself proves that automorphism group is infinite dimensional. You just add more points or add more Taylor expansion. And maybe something a bit more advanced would be that given another Stein manifold, S, which is small enough dimensionally wise. So 2 times the dimension of S plus 1 is less or equal to the dimension of X. Then there exists a proper holomorphic embedding of S into X. And this is by Anders. And what? And oh, sorry, it's also by Forsneric. This is Forsneric for Stein, and but only for the general case. So what does this mean? So maybe I should remind you that one of the many equivalent ways to characterize a Stein manifold is to say that it emits a proper holomorphic embedding into Cn for some large n. Okay, so instead of X here, you can take Cn, and this is a defining property of being Stein. So what we're saying here is that a Stein manifold with density property shares this line with Cn. So there's, just like Cn, there's some kind of universal embedding spaces for Stein manifold. Okay, so
actually you can say more. It's true in every homotopy class.
Yes. Yeah, so you start with any continuous one, if I remember correctly, of S into X, then you can deform that specific map to a proper holomorphic embedding. So, which of course for Cn is trivial, because then it's contractible. But here you can kind of incorporate topology of X as well. Yeah, so Stein manifold density property are somewhat universal in the sense of being embedding spaces in the real Stein manifolds. Okay. So with this, I hope I convince you that the Stein manifold density property have some relevance, have been studied, and they do interesting things. So it is worth looking for more examples and looking for more properties. So the rest of the talk will be devoted to proving that vector bundles over Stein manifolds with density property also have the density property. So let me give the theorem. So X, Stein, and density property. Then we take a vector bundle. Vector bundle. Of course, holomorphic complex vector bundle. And we need to assume one little more thing. So we need to assume that there is an automorphism of E. So automorphism of E as complex manifold, not as vector bundle, as manifold, which is not for fiber preserving, not fiber preserving, meaning that if you look at this, if you want to be very pedantic, it's not constant. For some X and X. Yeah, so what does this mean? I want really, so if you think that you have this vector bundle, so you have the fibers, the CNs, and I want at least one automorphism of the total space, which that's this. Yeah, this is just translations, but I really need an extra one. I mean, we don't actually know if we really need it, but we need it. Which can just do that. Okay. And okay, if you want to write it technically in this definition. And of course, the result is that then E as the density property. Okay. So, small note. If E is trivial, yeah, if is X times C to the R, I'll use R for this rank. Then this is already a result, is already a result of Rowling. And but in fact, it's in some sense two separate results of Rowling. If R is greater than 1, then this is a consequence which follows from Stein dp times Stein dp equal to Stein dp. So I'm making this schematic. I hope you understand what it means. It means if you take the product of Stein manifold density property, yes, it also has the density property. And but if R is equal to 1, it's also true. But you have to prove it differently, but different proof. Again, because C does not have the density property. When you have X and C, you cannot just say, okay, dp plus dp. And in fact, you know, when you have this situation, you can really think, okay, you have a product and one element is like this, one element is like this. You're like, well, okay, so if I need let's look at the first one, I just have vector fields which are somewhat parameterized by the other manifold. And here I have this vector fields which are parameterized by the other manifold. And then somehow you just make it work with parameters. But here, in this other case, when n equal to 1, when you have vector fields coming from C, well, to approximate a vector, this is all about approximation, right? So if you have a vector field coming from C, so let's call it vertical, then you really are going to need vector fields which are not vertical to approximate it. Well, here it is enough to use vertical ones. And I wanted to point this fact because we have the same exact problem. The proof for R equal 1 and the proof for R greater than 1 are different. And of course, in the case of rank greater than 1, we are going to use the fact that CR, the fibers, have the density property. While in the line bundle case, the rank 1 case, we need also horizontal vector fields to generate vertical ones. And this makes things more complicated. It works, but I'm not going to talk about it today because it really does involve quite a lot of technicalities. Okay. So I will completely focus on the case r greater than 1, and but I will point out, let's say, where we use the fact that the rank is greater than 1. So as I said at the beginning, I do want to get a bit into the technicalities of the proof of this theorem. But maybe before doing that, this is a theorem that lets you produce new Stein manifolds with density property. So maybe I want to give you a couple of examples that come out of this theorem. So we start with Danielewski surface. So this is the C3 with coordinates. C3 with coordinates x, y, and z. You take x, y equal p of z, and p is some polynomial. You need to assume some things about the zeros of this polynomial. The way this is not even a manifold, but okay, assume it is a manifold. So this is a Danielewski surface. Surface, and if the degree of P is greater or equal than to check, yes, X is not homogeneous, and it admits a non-trivial domain.
You mean strictly gradient?
Yes.
Otherwise, it's a homogeneous space of S.
Yeah. And it admits a non-trivial. Yeah, I think, sorry, degree 2, it still admits a non-trivial line bundle, but then it's homogeneous. And why do I want these conditions? Well, so the point is that I want to produce a new example, right? And the point is that, so first of all, I need a vector bundle which is non-trivial on some Stein space with density property. And then I also really don't want the total space to be homogeneous, because otherwise I'm not doing anything new. So in fact, this was not so. So the idea here is that the total space of the line bundle, total space, is probably a new example. What I mean here with probably is that, the list is not exact, like, okay, homogeneous spaces, and then there's this list of examples I showed you, but then there's even more, and like we're not really sure if this specific one is not appeared somewhere else, or it doesn't fall under some other theorem. But at least we made sure it's not homogeneous and it's not a product, so it should really be a new example. Okay, and maybe another example, which is more like a class of examples, could be, and this is the only algebraic geometry we'll see today, smoothly reducible fine variety. With only constant invertible functions. Invertible in the sense like 1 over f, right? So no zeros. And assume reductive group G X on X with an open orbit. And every time you have the situation, so you have this big open orbit, and then you have the complement, which is closed. And basically you say, okay, so this closed orbit, G also acts there, and he also acts with an open orbit there. And so you can kind of lower the dimension. And in the end, you will stop at 1 closed orbit. And we need to make some assumptions about this unique closed orbit. And it needs to be neither C nor C star to the K. Done. Access the density property. Yeah. And in these two results, one thing which I'm kind of hiding is where is this extra automorphism coming from? Yeah, so I claim that there is, I also need an automorphism which bends the fibers. And here, well, it didn't say why there is an automorphism that bends the fiber. This is another general result we have. It is that given a flexible manifold, whatever that means, and this is flexible, and this is flexible, any holomorphic vector bundle over it is also flexible. But you don't need to know what this means. I'm not going to write it down, so it's like I never said it. And I'm just promising you that it works. Okay, so I think now I want to move to the idea of the proof of the theorem. Yeah. Proof. So there are three main characters. Main. There's. So we have L. This is the Lie algebra of all vector fields. And vector fields are becoming VFS on E. Yeah. Or its density property is about Lie algebra vector fields. So this is our first main character. Our second main character is H. And this is the closure of the Lie algebra of the algebra generated by complete vector fields. Yeah, so this is kind of the two main protagonists of the story, because this is what the density property is about. Yeah, the goal here, final goal, is to show that H is equal to L. Yeah, L is all possible vector fields. H are precisely the ones that can be approximated by linear combinations of complete ones. Okay? So the final goal is to show that H is equal to L. So this is two of the main factors, and the third one is somewhat on a supportive role, and we call it P. And this is the Lie algebra of hyperserving vector fields. Serving vector fields. So what is meant by hyperserving? Well, here we are in the presence of a vector bundle. Okay. So something which is hyperserving is something which preserves the fibers. So you can think about it as something coming from the base plus something which only acts on the fibers. And when I say something coming from the fibers, something coming from the base, I have to be a bit careful. No. So the goal, of course, is to produce lots of complete vector fields. Yeah, we really need to show that H is very large. So I need to produce lots and lots of vector fields, which are complete. And the point of this Lie algebra P is that there we can explicitly find lots of complete vector fields. And yeah, so I was saying the idea is that you have some vertical components, something coming from the base. But this coming from the base, you have to be a bit careful. Because if you have a vector field, say, B vector field max, you would like to lift it to a vector field in E, which is pi per circle. And so to lift it, I need the automorphic connection. So I need to choose a horizontal distribution. And holomorphic connections don't always exist. But here we're lucky, or maybe we're just in the right situation, because the obstruction to the existence of a connection is cohomological. And the connections are you can always see them as some sections of some specific endomorphous bundle tensor omega 1. And the point is that on Stein manifolds, cohomological instructions are valid. Yeah. So on Stein manifolds, cohomology is true. I mean, not homology in the sense of, okay, so this is maybe a strong statement. Homology of coherent analytic sheaves, coherent sheaves is true. But a bit too strong. Yeah, so not all homologies, of course, we need some topology in there. But if you take a homology of some coherent analytic sheaf, which in practice often means sections of some bundle, then this homology is trivial, and this the existence of this connection lies precisely in a homology of one such sheaf. So there is no obstruction, the morphic connection exists, and we can lift things. And furthermore, and okay, this you have to check, if V is complete, its lift to B is also complete. Yeah. So now we really have a notion of vector fields coming from the base. Take a vector field downstairs, lift it upstairs, and if you start with something complete, whatever you get upstairs is also complete. And this operation is also continuous, which is also nice to have. So okay, so now we have a meaning of vector. Okay, vertical vector field, I think it's clear, just means that project to 0. And horizontal vector field is what I mean, just something coming from the base. Okay. And the first step in the proof is to show that P is contained in H. Yeah, so every hypercertain vector field can be approximated by the Lie combinations of complete vector fields. Yeah. And so this is what I was saying before, that to prove something like this, you really need to show that there is lots and lots of complete vector fields. And our first step, our first big family of complete vector fields will come from P. Yeah? This is what this is about. And so if you're given, let's say, a vector field in P, we can always write it as a sum of a horizontal component. Horizontal now really meaning that coming from the base. So VH is the lift of vector field X, and VV is vertical. Yeah. And I'm going to approximate these two separately. So I'm going to approximate the horizontal vector field using horizontal vector fields and the vertical vector field using vertical vector fields. Complete. And this is maybe the first time we notice that we really need R greater than 1. So the rank needs to be at least 1, because there is no hope to approximate vertical vector fields using only complete vertical vector fields if the rank is 1. Then you really need a mix of it. But let's start with the horizontal, since we already did most of the work. So the horizontal part, well, you just approximate, so you push it down. And what is the push down? Is this. This is also the same as this. Maybe I have to get more idea. So this, so you have your vector field B, you push it down, and you know, the fact that it's pi preserving is really important, is that this is in fact, you can see this as a vector field on X. And X is a semi-manifold with density property. So there we can approximate with the complete vector fields on X. And again, this is density property of X. And then lift the approximation. Lift the approximation. Yeah, that's the basic idea. You go downstairs, you approximate all you have to do downstairs, you go back up. And in fact, this new thing will approximate the initial one up to some vertical component. But the vertical component we deal with later anyway, so we're happy with this.
But however, I basically don't understand the setup. So first you were saying that P are the P preserving vector fields. Are these vertical?
No, you're also perfectly fine with the automorphisms of E, which permute the fibers, that move the fibers.
Yeah.
So not pi preserving,
yeah. Okay, fine. But how are you then decomposing?
So any vector field in general, you can decompose as once you have a connection, holomorphic connection, you can decompose it as vertical or horizontal, right? And it turns out that if you start with something which is pi preserving, the horizontal part is really the lift of something coming from below.
Okay.
And the existence of holomorphic connection is, I mean, we can do it with Stein manifolds.
So that's cohomological. Yeah. Okay, fine. Thank you.
Okay. So in fact, this is already, yeah, this is fine. Now, horizontal part, we can approximate up to vertical, but you know, I mean, the vertical part we'll deal with separately. So let's deal with the vertical part. And this is much harder. And okay, let's take a look. So here I already kind of started with a vector. You know, what I really have to do is take a vector field and show that I can approximate it with the combinations of complete vector fields. Here, I'm not going to do that immediately. Like, I'm not going to start with a vertical vector field and try to approximate it. I first of all just want to produce lots and lots of complete vertical vector fields. Okay, and then I will show that using this I can approximate anything. Okay. So we're producing vertical vector fields. Fix a point and take a vector field, which is complete, on the fiber. Yeah? And remember that it is there. Yeah, so this is really, you only look at the fiber and you take a complete vector field there. Okay, so this is not a vector field on E, it's really just a vector field on one specific fiber. And the claim is that we can extend it to something complete everywhere. So this will be at complete vertical, that's important. Complete vertical vector field on E. So this point is a global vector field, which extends. Yeah. So you can prescribe a vector field on a fiber with complete ones. That's also important. And how do we do this? Well, we basically employ a trivialization. No, a bit defined now. Fix. So we fix trivialization. So these are global sections. global sections, sigma 1, sigma r, that generate at this specific point that we have. These are basis of trivialization. And define from the trivial bundle x times c to the r into E that takes a pair Q, V. Q is a pointing x, V is a vector, and we sum it to f of Q, and I will tell you what is f in a moment. And then you just take the linear the corresponding vector according to this trivialization. Yeah, if you forget about f, which also need to tell you what it is, this is just the trivialization. Point is that it's not global, right? This is a trivialization of P, hence is a trivialization in all complement of an analytic set. And this f is precisely the function that defines an analytic set, where f is our automorphic function from x to t. Such that f is equal to 0 if and only if sigma 1, so maybe f of q is equal to 0, if and only if sigma 1 of q, sigma r of q is not a basis. So I'm going to write this like this. Okay, so alternating product, kind of determinant. No? So if these do not generate, then I'm going to set f equals 0. And these are the set where they do not generate some analytic set, so it exists. And so the idea here is that wherever you have a trivialization, you use the trivialization, right? You can just say, okay, I take the vector field, like let's say if I have a vector here in CR, I take the corresponding one on the trivialization. And when I'm not generating, where this trivialization doesn't work anymore, I just set it to 0. This sounds very discontinuous, but in fact, since I'm multiplying, it's not. Okay. And the nice thing here is that this is also a vector bundle, and you look at vertical vector fields here. Okay, so you think you have your flow, you have your vector field here. You can simply transfer it to the other side. And if you had a flow on CR, you would now add a perfectly fine flow on E, and you would know it's complete everywhere but where f is equal to 0. But where f is equal to 0, the vector field is pushed to 0. So that's also complete. So let me write down what I just said.
How can you have that f is 0 even only if it's always analytic?
Yeah, sorry, it's one direction. I mean just this, yes. Yes. So,
And f not 0, not 0.
yeah, and f not 0. And not.
I have one more question from the line above. The line where V is complete, then its lift is complete.
Yes, you have to check. You have to check.
Is that because of some kind of linearity of
The
connection?
yeah.
Okay.
Yeah, basically if you look at the local, let's say that have coefficients.
So locally it would give you vertical conformance. It's linear.
Exactly.
We also want
Yes. Okay, maybe we're gonna assume that would be different. So it's not a 0 function, and at that point we're good. Okay, so how do we, so what I want to do, why did I do this thing, is to transfer vertical vector fields on the trivial bundle to vertical vector fields on our bundle that we're setting. So what is a vertical on X times CR, let's say that X has coordinate Q and Z, looks like PI Q Z B in ZI. Yeah, I can really use coordinates because this is just the product. So this is what it looks like. No, you can think about it. So if you forget Q, if you fix Q, this is a vector field in CR. Okay, just any generic vector field, and somehow parameterized by Q. That is in fact what you do when you only have the product and you don't have a vector boundary. And then using this math, this goes to, so let's say use phi, maybe star. Maybe star, I think it's the standard notation. This would go to F of Q, and then we're going to use this funny notation. And here pi of Q D D ZI. And so, oops. And so, yeah, this tensor here is to really make you think that in the end these flows are all vertical. Like, so sure, these are vector fields, but if you try to think about their flows, there is, it's equivalent thinking of vector fields or thinking of flows. You really only vertical stuff. And here, what I'm saying is that I'm taking really the same exact thing. Okay. According to this realization, where I can, if I cannot, just set it to 0. So you see that if we start with something complete, so if the flow is defined for all times, this is also perfectly defined for all times. If I start somewhere where F is non-zero, then I just flow as if I was in trivial coordinates. And if I start with something where F is 0, well, I'm 0, so I don't need to do anything. My flow is constant. Okay. And yeah, okay, so, and then you can simply choose your P. In fact, your PIs are not even going to depend on Q once you use one of the bits. If you start with only one complete vector field on one fiber, Q doesn't appear here, and you can take it constant in X and sometimes. Okay, so here I produced some, potentially a lot, of vertical vector fields. Okay, and in particular, at the point P, they span the whole tangent space. And if I change P, I can generate the tangent space at any point. I'm not going to be able to use only R vector fields, I'm going to need more, but that's perfectly fine. So this way, you obtain complete vertical vector fields. A1 in some large n a priori, such that A1 Q, A and Q span everywhere. So spanning Q for all Q in X. Yeah. And so I really want to use the Dex Stein. And we already saw one key aspect of being Stein is the Cartan theory B. It tells you that cohomology has no issues. So if you have a surjective map of sheaves, this is always surjective at the level of global sections as well, which is something very strong and very nice to have. So we consider the sheaf map that takes n holomorphic functions of X, this is the structure sheaf of X, and sends it to vertical vector fields of E. So I'm considering this as the sheaf of vertical vector fields in E. So some set of just vector fields in E. And we take an n tuple and we send it to the sum. So these are complete, these AJs are complete, and they're vertical. And these AJs really come from the base. Yeah. So maybe to be more precise, to do this. Yeah, because I want functions on E. But the point is that these functions, since they really come from the base and these objects are vertical, these functions are in the kernel of this. Right? They don't see verticality. And in fact, this product is also complete because of this reason. Okay. So all of these elements here are in fact linear combinations of complete holomorphic vector fields. So all I need is to prove that this map is surjective. I need surjective on global sections. Yeah, because I really need vertical vector fields defined everywhere. So that's why in global sections. But as we said, because we're Stein, this is equivalent to local. So this is equivalent because X is Stein to just prove this surjective. And for a map of sheaves to be surjective is really more of a local question. You just need the Stokes surjectiveness. And it kind of seems we're done, right? Because you're like, well, but this spans CQ at every Q, so this is surjective. No, actually not. Because the sheaf of sections is not enough to generate every direction, right? You also need to generate like the area orders. So problem, it is not enough to span Q. Say with, if you were locally, what you would be using would be this, no? Like locally to span at a point, you would be using simply this vector field. You have R of them and you span every direction and you're happy. But you also need the higher order terms. So you also need higher order terms like ZA to the alpha in CI, where alpha is our multi-index. Yeah, if we can generate all of this, then is fine. Then we're good. And it's possible. I'm just going to say it's possible. You have to consider basically instead of taking the sheaf of vertical vector field, you have to take a sheaf of vertical vector fields of a specific degree, and then redo this argument here instead of saying, okay, I span, sure, for degree 0, you just span the degree 0 verticals, which in fact is this. Or this is isomorphic to this, and then you're like, okay, now I have degree 1 vector fields, and then you span the degree 1 vector fields, and you do the same argument. And you do it for every degree. Okay, and in fact, the number of vector fields you're going to have at every degree is finite, but then when you have all the degrees, you practically have infinite many. It's also really important to go by degree to make sure you cover everything. Okay, so you see now that we have plenty of horizontal complete vector fields. We're very happy with them. And now we also have plenty of vertical ones. In fact, we have all of them, if you believe this degree argument. So in the end, what we finally proved is that P is contained in H. Yeah, all my pi-preserving vector fields, for one reason or another, can be approximated by complete vector fields. And that is already very nice. Now this is where our assumption comes into play. If you remember in the theorem, we have to ask this extra thing that there is one automorphism which does not preserve the fiber. And why? Well, because then we have the another theorem. And this is very general. So you take vector bundle, X Stein. So we kind of forget, this is a general statement. We don't need density property anymore. And again, L is all vector fields, and P is pi preserving. And then H tilde, meaning this would be any Lie algebra. Here I'm using the same names for the same Lie algebra, but here it can be any Lie algebra, which is closed. The algebra, which sits in between. Yeah, if you have a Lie algebra, let's say it sits in between, and let's say it's not P, then it must be L. Yeah, as soon as you have one vector field, which is not pi preserving, and all the pi preserving ones, you in fact get everything if you assume closed. Okay. And this automorphism, which bends the fiber, is made precisely to ensure this condition. Once again, I arrived precisely at this theorem, just like last time. And I will force you to stay here 3 more minutes. Just to say that there is one very important character here. So there is a new character in the proof of this, okay, which is theta, which is the Euler vector field. Which is what locally you can think of something like this. So in the fiber, so if y are the coordinates on the fiber, the flow of this so induces this direction. So the flow of this is basically just homotopy in the fiber direction, okay, not doing much. But why is this useful? Because this action induces a notion of degree on vector fields, which is really what you would expect. You know, vertical vector fields are basically vector field on Cn. So they kind of come with a degree, but you somehow need to make this notion of degree global. And this is where this comes from. So it induces degrees. And now having these degrees, in fact, through maybe some 15 to 20 minutes more work, will give you this final result. Okay. In a very similar way, actually, to how the Anderson-Lampert theorem is proved for Cn, where you really go by degree, and you do the same, is that the degree is something a bit more abstract. I'll conclude by asking a couple of questions. So the first one, I think maybe you already have in mind, is do we need the existence of an automorphism? Yeah, is this, maybe this is for free, you know, in the case if your base was flexible, whatever it means, this is for free. So this could be for free. It's unclear. And the other question is, well, I said that one thing we used a lot is that the fiber has a density property. In fact, we really use that in CR a lot, so this notion of degree. So maybe the question is, if I have another vector bundle, and X is tiny p, and the fiber also is tiny p, does it mean that P has tiny p? Yeah, so do I really need Cn or just any vector, or any, sorry, definitely not vector, but fiber bundle? Or is any fiber bundle with Stein fiber, with the density property fiber, really density fiber? So if anybody has answer, welcome that. Otherwise, thank you for the attention.